move on to the next portion. We have now our panel review, and the way we're going to start it is Tom Myers, who's our primary hydrogeologist, has some slide presentations with his comments on it. And just to remind everybody, Tom is a researcher and consultant in hydrogeology and water resources. He got a BS degree in civil engineering from the University of Colorado, MS and PhD degrees in hydrology and hydrogeology from the University of Nevada at Reno. So Tom will start us off.
Okay, thanks, Kirk. I'll start off. I've got a presentation here that I put together upon reviewing the EBD that we've been talking about for the last 2 days. And some of what was in that EBD has been updated based upon the presentation we just saw here. So I may have to jump around a little bit, not jump around, but I may skip over some things I had written in here because it's become apparent that they've already been taken into account, or they've already been changed. I wanted to start off by backing up a little bit and just talk about what the purpose of the way I looked at the documents and what the purpose of reviewing all this data and all this modeling was. And that is, there were two main things. I mean, we know there's going to be the development of a pit, whether we know the exact size and layout or not. But in order to develop this deposit will require an open pit. And so I'm looking at all of the hydrology from that perspective. And two, I'm looking at all of the hydrology from the idea of tracking contaminant movement from the site and so where contaminants would end up. So I've tried to look at everything in that perspective and to answer questions such as, is there sufficient data? Has it been appropriately collected? Has it been analyzed correctly? Conceptual models, are they realistic? And does it reflect the data? Is the water balance accurate, or how could it be made better? And then is the groundwater model appropriate to the site? And it's in these latter two things that the reports have changed a bit, so quite a bit. So I mean, some of the comments I have are still relevant, and some of them I will actually skip over as a result of what I saw before. Briefly, I don't think we've actually talked at all about what mine dewatering actually is, and I thought I would just give a page or two or a slide or two of discussion on what we mean by mine dewatering. I mean, when you build an open pit, when you construct an open pit that goes below the water table, the water runs into that, will flow into the pit, and in one way or another, you have to remove the water that flows into the pit from it in order just to keep the mine dry and actually work in the bottom of the pit. And so the questions that we're asking are, what kind of a drawdown would you expect from dewatering a pit? Well, I mean, at the pit, of course, you're going to have to lower the water table effectively to the bottom of the pit. But the question becomes, how far does that drawdown affect things away from the pit? Is it is it just a couple of, a mile, like one I've been looking at recently in Arizona, it only goes about a mile away from the pit, or does it go 35, 40 miles like a couple in Nevada have done? So those are questions that require a good groundwater model and a good understanding of the deep groundwater connections, both in the bedrock, within the bedrock itself, but also connections of of groundwater in the bedrock with the surface. Now, I have a picture here that shows a little bit about what dewatering is. Just a general outline of an ore body here. You got to construct an open pit to get to it. You have the pre-existing water table, and as you develop the pit, and you get to this water table, you can purposely lower the water table to keep the pit dry. I mean, this cartoon here basically shows what dewatering is. In this particular instance, it shows that they'll use dewatering wells. I mean, it's hard to say at Pebble whether there would be dewatering wells, whether it would be low enough to just pump it from the pit as it flows in, or what. I mean, they're nowhere near that point yet, and I don't think the bedrock has been characterized sufficiently to know whether that's to know how they would do it, or it would probably be a combination of both. As we said earlier, water balance and groundwater model are intimately connected, and so I'm going to start by talking a little bit about the water balance as I had reviewed it. And I mean, the water balance is basically it's very simple. I'm going to start with the bottom first here, or with what water balance is. Inflow equals outflow, or inflow minus outflow equals a change in the amount of water that's in the system. It's just sort of I mean, if inflow equals outflow, there is no change in storage. The goals here in this water balance, as I understood them from reading the EBD, were to calculate runoff and recharge, which is a sum of the precipitation and snowmelt. That's what that R and SM stand for. The sum of that minus the amount of water that's lost from the system. It's the evapotranspiration and then the change in soil and the change in soil moisture. Now but these things are intimately connected, and so solving it, it sort of almost became a circular analysis. And I'm not going to go into the details on that, but I do have a couple of questions and a couple of things that I wanted to raise that hopefully after my presentation they may respond to, raise them later or respond to them after I come up. There were some uncertainties in the water balance as I saw it. Precipitation is, it's rain or it's snow. But the model has to consider whether it is rain or snow, because they were simulating recharge on a monthly basis. And if it's snowfall, it's obviously not going to, unless it melts, it's not going to be rain, it's not going to be recharged that month. And the model called it rain if the average temperature was greater than -2 degrees Celsius, and it was snow if it was less than -3 degrees Celsius. And the question I have is, the average temperature is for the overall month. Now, in a month like April, you may start out very cold and it's all snow, and it transitions to rain. And I think that this particular portion of the water balance could lead to a lot of uncertainty, especially in a month where it starts cold or ends cold, where you have a lot of both snow and rainfall, and that'll be something that I think could lead to uncertainties in the water balance simulation. The same for snowmelt itself. It was a simple relationship based on average temperature, but what about a period where that average temperature is a lot higher just due to a very warm period at the end of the month? That could lead to a lot of errors in the estimate of snowmelt, and at least in my understanding of how this was done. So those were a couple of points I wanted to raise. But then the water balance is solved by calibrating and adjusting various precipitation and various factors. I would say the one problem I had in reviewing this is I was not provided with monthly data. I had requested monthly data to review the water balance, and I never received it. So I was hoping to be able to, because there are a whole bunch of factors that went into the calibration of this, and I was unable to evaluate whether the adequacy of the calibration, because I wasn't provided with the data to do so. So that's a problem that I wanted to raise. We were supposed to kind of come up with an idea of evaluate this stuff and ask questions, but I was unable to do that in total, except for the questions that I just raised up here on this other chart. So potential evapotranspiration, that's evapotranspiration that would occur if water is not limiting. One of the questions I had, one of the methodologies that they used in the water balance was that they reduced it to 50% or 90% of the calculated value based upon whether it's upland site or a high evaporation site. I don't know why that's done, because potential is the total ET that can happen based on moisture not being limiting. So why would you introduce a factor based on moisture being limiting, if indeed it is potential? And in the report there was no reference provided and there was no map provided as to where these sites were, so it was unable to evaluate that. Then actual evapotranspiration, that's what goes into the water balance. It's defined based upon, it's defined according to the soil moisture availability as a function of the total soil moisture holding capacity. Now that's a very complicated thing, but effectively, PET was reduced again by either 0.5 or 0.86, depending upon whether the site is, as I say, most sites or a high ET site. It appears to me as though the potential evapotranspiration is reduced twice here, but it wasn't very well explained. So I'm hoping to get that was one of the another uncertainty. And soil moisture capacity was either 4 inches or 14 inches, and that's based on whether it's a moist site or a high ET site. And that was done without reference or with any mapping of where this provided. I mean, where this was. So those are a couple of fairly critical statements that I had here. This was a result of the monthly water balances. We show. They showed some very good water balance. It appears as though a lot of this has been updated over the from the time this was done here, because I mean this is for the site SK 300C, the one that includes a lot of the dry conditions. And I'm sorry this doesn't show up really well. I had to get it. I did it with a screen capture from the computer. But here's an example of where the where the monthly flows don't match so well. I believe that this one here is simulated. The red one here is simulated, and the blue one is measured through the water balance. And there's actually quite a large difference at the low flow end of this one, because this is a logarithmic scale, which means that this line is a 1, this is a 10, and it varies. So basically this is saying that, for less than about 30 months there, the distribution shows that there's quite a big difference in the low flows in the simulated versus the measured low flows at this site. So this raises questions in my mind about the water balance, how well the water balance was done. Now, it also appears as though it's been changed and it's a lot better. So I will say it appears as though a lot of my concerns on this have been taken in, may have been taken into account. But I'd like that, to hear what, actually that's something we might want to talk about, is how you've changed it since this was done versus the new one, because it appears as though it looks a lot better right now. Now I'm going to switch directions a little bit. The open pit would be constructed into bedrock, and the properties of that bedrock will effectively control the effect that bedrock or that dewatering will have. I will say that I've never seen so much data collected on bedrock in my life. I've been working on mine. I've probably worked on 25 different mines, and there's as much data here as a sum of most of those. I mean, this is really good data that has been collected. Packer tests, response tests, the multi-port sampling. I mean, that one deep well they drilled had the ability to collect water levels at 50 different points, and then the well next to it, the ability to pump. I think from 7 or 8 different levels, and I mean that's some of the cool. Dare I say, the coolest data for a geek I've ever seen. And I know of a couple, of a few other situations where I now can come reference this, and it's like, see, it can be done, folks. And they may not, Pebble may not, this is one of the cases where other mining companies may not like you because you've done something that I've been trying to get people to do, because I'm reviewing these things all the time, and this is really good information. So they may not like you. and some of these graphs we've already seen here. I mean, the Packer tests show a variation, although I think this one's slightly different than the one you used, but it does show that, at depth there are areas that have relatively high conductivity. And by the way, I was asked before, just, for the purpose of for the audience and whatnot, to explain possibly what, we use the word conductivity a lot. That basically is a reference to the ease of flow, how it's got a technical definition, but the higher the conductivity, the faster water will flow through the site for the same amount of slope. If you think of a stream, it's controlled by the slope. But if you have units, a given slope, the more porous the media is, the more water that will flow through it. And some of these low values over here, sort of an aside, I hate the units that were used here. Meters per second. I can't think in terms of seconds. Why do you guys use seconds? Meters per second. But 10 to the minus 8 meters per second is really, really tight. I mean, very little flow goes through it, whereas 10 to the minus, what is that, 10 to the minus 3 or 10 to the minus 5 over here, that's like 3 or 4 feet per day. So, I mean, convert it to something that I can think in terms of, it's really stuff, you know, that's pretty conductive. And some of the stuff down here in the bedrock, and that's at 2,500 feet. Now, it's a fracture zone, but that will allow flow, quite a lot of flow to happen at 2,000 to 3,000 feet below the surface. Here's another figure that just shows that there wasn't a lot of variability between types. In fact, if I'm reading this correct, these right here are some of the fault. Those was measured in faults, and what you can see is that it's a relatively high conductivity. They were unable to differentiate between types of bedrock and overburden as far as the measured conductivities. And this is my favorite one. I mentioned the multi-port sampling a little while ago. This looks very complicated, but what this is different dates where they measured the depth of water in all of those 50 different ports that I referred to before. And this shows you that you have a down, let me say this right. I mean, it shows areas of a downward gradient, meaning that flow can go down. It shows an area of artesian pressure around one of the, or I hope I'm not saying that backwards. Around the fault zone here, I think they call it the ZE or the zeta fault at about 1,500 feet. This just shows, this is the kind of information that is really very, very useful in considering the flow in the bedrock. They have, I mean, one of the conclusions was that there's not much seasonality, meaning that things don't change much or don't appear to reflect the change of seasons at depth, but there is quite a lot of variation down there, more variation at depth than I'm used to seeing. You want to refer?
Yeah, if you look at the top 600 feet, that whole variation is seasonal variation. But once you get below 1,500 feet, if you look at those timelines, it goes from highest at earliest, and it just continues to drop over the whole time period. Okay. So there's a huge variation, but what it's showing is a very slow drainage of conditions that were applied as a result of drilling and installation.
So this is dropping from about 2006 through so over about 2 years, you've got about a 15-foot drop there.
That's correct.
Is what you're saying. Okay. Okay. This is kind of a summary here of the deep bedrock sampling, and I'm just going to jump to the bottom here and ask the question. I say here, there is no data away from the pit necessarily, and all of the data that's been collected is within the deposit. And let's see. Now, further down, I mentioned you mentioned compartmentalization. I'm going to bring this up again. I'll wait and bring I've got a slide a little further down where I want to mention a couple of other mines that were said to be compartmentalized and possibly weren't. So I'll just bring that up in a little while. Groundwater modeling. We talked a little about groundwater modeling. Why do we do that? Why do we model in the first place? Basically it's so that we can take what we see on the ground and make predictions with it. They've got a really good site description out there with a lot of data and a reasonably good conceptual model of where the flow goes. But we want to figure out what happens into the future. So you have to put it into the computer and use mathematics to solve it. That's what a groundwater model does. It's basically an attempt to model the flow descriptions and rates that that have just been described. I was going to say that a couple of details. I have some details about the modeling that may not have been brought up before. I wanted to suggest, first of all, they use a model that's called ModFlow Surfact, and I did want to say that that's an adequate model for this job. You're still using ModFlow Surfact, is that correct? Good. I was going to suggest, I would suggest, and you probably are now, using the stream package and a few things like that. That would be, yeah. So I've got suggestions here that they're already using. How about some of the lake packages?
I've not incorporated the lake package yet.
Okay, and I know you're not doing ET, but
That's right.
I'll. Now, I am wondering about the domain now, and that one of the things usually, usually we like to go to a no-flow boundary or to a boundary that we have some flow over. At least that would be my suggestion. And you said they wanted to go far enough away that you didn't overly constrain the boundary. But yet these boundaries here, and I'm just gonna, I guess it's the reason I had. The reason I wanted to ask about this is what was done here was that this whole the model goes a long ways away from the site, which is fine, but there's a flow boundary across that whole thing, and meaning that there's no constraint, as I see it, on the flow. A no-flow boundary would be one where you would go to and you know there's no water that's going to flow across that direction. The other choice would be, in my opinion at least, the preferred choice is to use a no-flow boundary and also to use areas or go to areas where you have a constrained cross-section that you could say there's 20 CFS crossing this section here, and you can use that as a target. And that would have been my suggestion in this here. And although if we don't do that, then there should be you should present, I think, what the flows are all the way around here, so we have some idea as to whether there's some area that a lot of water is coming into or going out of. Because I have reviewed models and I've seen models and I've been commented on in doing this kind of thing. Exactly what I'm suggesting right now is that the problem is that this can allow a source of water into the model that helps to balance things in places where there really isn't any water that should flow into the. And I don't know that's happening here, but I'm suggesting that you show otherwise, or that it's not. I think I've just covered that. And here I'm into the bedrock, and this is actually back from when you had only 5 layers in the model. Now there's 7 layers in the model. It would appear as though, this is a cross section through the model. And it shows that at depth, there's just one layer at depth with one conductivity, and I guess I'll ask you to explain after a bit if that's changed at all, because the lowest depth, the lowest layer had just one value in what I had reviewed, and I wanted that's not ready to simulate dewatering, I guess would be my point. And I'm going to skip that. Calibration, at the point I saw it, there had been no automated calibration, no use of PEST or anything like that. No weighting of the head values or the targets or anything. And
do you want to just explain what model calibration is?
Model calibration is basically the process that one goes through to make sure that the model says the same thing that nature says, that the modeled values are the same as the observed values. And that would be the water levels in the aquifers, and it would be the flows through the aquifers. They talked, the presentation before showed how some of that stuff matched. And I believe that it's a lot better than the version I had reviewed, as we'll see in just a second. But there are methodologies for calibration, and there are automated methodologies that you can use that are designed to minimize the error. And the version that I had read did not talk about having done that. And they've got some of the best data. As I mentioned, this is some of the best data I've ever seen, and it's prime for doing automated calibration. At least I would think so, because the weights should all be around 1. I mean, you constructed all of the wells, and so there should be few issues around errors in the observations. When I'm talking about weighting something, it's like, how good of a measurement is it? I mean, if the measurement is uncertain, you don't want to rely on it very much, but you don't want to just throw it away either. It is data, and therefore you should use it, but maybe not give it as much of a weight as you would a really perfect measurement. So what am I doing here? About 20 minutes? Okay, just a couple more slides. I should be. I should be okay then. And sensitivity analysis. There was no sensitivity analysis done either. I was going to mention that I did make a comparison of some of the calibrated Ks, and I'm just noting that calibrated K being greater than some of the observed Ks is not unusual. Almost every model I've ever done is that because of scaling. I mean, when a model considers an area, whereas a pump test is effectively a point, and you would expect this. And so that's an aspect of this I found to be. I expected to see that. Why is layer 5 just 1K zone? I guess the inflow to future pit, and maybe you'll address that after a bit. And here, see, here I was asking the question bias and residuals. What this shows here is in the model that I had reviewed, it shows that a great many of the observed values in their layer 4 did not land on the one-to-one line, whereas the figure we saw before, they almost plotted perfectly on the one-to-one line. And the residual statistics are much better than what would result from that. I don't even recall seeing a statistics in the original, in the one that I had reviewed actually. This shows a bias because, as you can see, it's all on one side, and it was explained in the report as being, well, these were up on the upland, and we focus more on balancing the values and the discharges to the streams. And with a bias like that, though, the flow as it comes from the uplands and it flows into the valleys, if you don't have that accurately simulated, I mean, this suggested that wasn't accurately simulated, which means that the conductivity values from the model may not be accurate, and that could have an effect on the long-term predictions from the model. And here's just one more example that showed the residuals. Again, I doubt this is still occurring, but it showed I felt this showed a bias. They were increasing with time. This is one of the worst examples from the report, but it showed that that they were increasing with time. And here's the question that I mentioned earlier, and it was one of the conclusions of the presentation, and something I hadn't read at all about in the reports. Compartmentalization, where the faults, because of the faults crisscrossing and some of them conducting flow and some of them being a barrier to flow, that it will basically segment out the bedrock so that so that you don't end up with connection within the bedrock. I mean, as I said a little while ago, only the bedrock within the pit has been characterized. I'm not sure we can extend that characterization beyond the region of the deposit because the geology does change. And I think that might be a data gap that Pebble needs to somehow fill in because the potential for dewatering is huge. And I've mentioned two mines here. One of them is called the Robinson Mine, which is in the eastern part of Nevada. This is a place where the model relied very heavily on dozens of both geochemical data and well data to show that there were half a dozen different compartments, and they predicted almost no dewatering effect more than about a mile from the mine when they reopened it here. And there are two springs 10 miles away that have gone dry that are linked to this. And so whether they could have characterized away from that point or not to show that to prepare for that, that's one issue. And I mentioned the Gold Strike mine, which is one of the largest gold mines. It's in northeast Nevada. In 1992, the model had predicted a dewatering rate partly based on compartmentalization and faults of less than 10,000 gallons per minute, and in 1998 they were pumping at 72,000 gallons per minute, over 100,000 acre-feet per year. And again, that was that kind of difference here, that kind of potential error here, I think would be more problematic than it was there. I mean, they ended up with tracking drawdown 25 to 30 miles away from the Gold Strike pit, but there was also a fault that helped to compartmentalize their dewatering from an adjacent mine's dewatering, and so I mean, literally, you can see a drop of 500 feet across the fault after pumping. So it's a perfect example of conductance along a fault and the fault acting as a barrier. And if that's the case here, that's great. It'll make it easier to construct a pit if that happens. But relying on it and finding that it's not the case, I don't think you want to be planning for 10,000 GPM and having it turn out to be 70,000. That would be a disaster here. I think I've summarized it all. Yeah, that looks fine. So let's.
Would you like to make any more responses now, or shall we have our panel come up?
I'm easy either way.
Okay. Well, let's go ahead and have our other panel members come up, and while they're doing that, we'll give brief introductions. That's Tom Al, Katie Walton Day, and Chris Way Thomas. And just do a quick intro. Katie Walton Day is a research hydrologist and water quality specialist for the USGS in Colorado and Denver. She has a bachelor's in geology from Smith College and MS and PhD from the Colorado School of Mines with a minor in geochemistry. She's been working for the USGS since 1984. And her primary area has been the hydrologic and geochemical processes affecting metal mobility in wetlands, streams, and groundwaters affected by acid mine drainage.
So once again, we have Chris and Tom. Chris Way Thomas is a surficial geologist here in Anchorage with the Alaska Volcano Observatory. His expertise, geomorphology, hydrology, quaternary geology, and specifically looking at hydrologic hazard assessment associated with Alaska volcanoes. Dr. Tom Al is a professor at the Department of Earth Sciences at the University of New Brunswick. He's our geochemist on the panel here and has expertise in geochemical and hydrologic studies of mine tailings and waste rock and the release of contaminants into groundwater and their transport. Do you guys want to respond directly right now with what Tom had brought up, or do you want to? Seems like we should finish a bit of this discussion if you'd like.
I brought up a lot of points. I don't know how, and some of them. I'm sure some of them are just things I didn't, see in the report, and they'd be very quickly or easily responded to, and maybe some of them aren't. I don't know how we want to do it.
Is there anything specifically that you felt, Rod, or
I don't think I have anything specific. If you list the points, I think we can respond to them. The ones that you want to at this point.
I may not remember them all. They were all like some. That's why
I'm trying to put it back to you, because I don't remember them either.
Well, what about the idea? What about the idea of distribution of rain and snow by month? I think I have 2 points in that regard. Well, I think that could be provide a fair amount of uncertainty to the water balance model, both on the transition months like October and April.
Well, of course, I work a lot in areas that have snow, and it is an issue, and it's an issue in every job I've ever been on. And in any given month, indeed, you can be out. We use average temperatures, and if the average temperature is 2 months, you could have plus 10 and minus 10 in that month. And whether it's at the beginning or the end of the month will make a huge difference on whether you're creating snow or melting snow. So that's real, and is part of the analysis. It just simply is. So we adjust those temperatures when we're doing our calibrations, and we see, for example, perhaps that 4 of the 5 years that we're looking at all have not enough snow generated in November. So we move the number a bit and to try and make it a little bit better so that it kind of averages out. But it will always be there using those kind of monthly averages.
So you do kind of like a sensitivity analysis then?
Yeah, I guess so. You have five years to work with, and so you move the number around and you look at the impact that you get from it.
The same applies to the snow melt. You're still using the equation, was it 3 times T minus 1?
Yeah, I'm not so excited about snow melt, and the reason that I'm not is that snow will melt. I do still adjust the number to try and get it to come out right, but it doesn't impact our analysis that we're doing so much, whether I get 50 or 80% of my snow coming out in May or the rest of it in June. I'm still getting that volume. It's the snow manufacturing that's way worse because I might I'm either, say in November, I'm either creating rain and so I'm getting the recharge in November, or I'm making it snow and I'm transferring that to the spring. So that's a way more critical one than.
But, I mean, except that we're turning it into recharge, which then Hugh is running into, you're trying to balance, heads on a monthly basis, and at least in the uppermost layers, it's gonna go right to it. So that's hence it's a source of uncertainty.
Yeah.
To the groundwater model.
Yeah, it's a source of uncertainty that we're also starting with precipitation from Iliamna, and of course that's not exactly the precipitation we're getting on site. So again, we have to know what we're doing here and how we're going to use it. It's not going to be an exact fit. It's going to be getting the distributions right, and the distributions that we expect. So you do have to be careful how you're using the stuff that you're generating.
I was just going to ask, with regard to the switchover between snow and rain, if you considered or have played with some kind of sensitivity analysis to look at the range there of how it affects the model.
Well, yeah, for myself, but it's nothing ever that I've given to anybody else. So,
but would that be a helpful thing?
Well, it might help other people understand what the impact is. Yes, yeah. It's something that, of course, the people at Night and Peacehold are very interested in too, in terms of how they go forward with their any kind of water management schemes that there will be requested to generate as mine planning progresses.
Yeah, actually, that's a good point. This water balance and getting this stuff accurate. I'm thinking about it in terms of recharge to the groundwater, but it also becomes input to the model, to the design of a tailings impoundment and stuff like that. So that becomes very important. What am I just confused about the reduction of PET by 50% and 90%? I mean, what can you explain what that is?
I expect that I didn't edit the text right.
Okay.
Because I certainly didn't diminish it twice.
Well. But why was it even PET, though, is assuming water's not limiting, and this appears to limit it.
So I used a methodology to generate PET, which is Thornthwaite, which is really generated for continental United States, an empirical method. It's not generated for Alaska. And so on my early runs, I had some very high PETs, and they just didn't match other people's measurements of evaporation in the north, nor the pan evaporation data that we had on site. So in discussions with Jamie, we really didn't want to have that much, our AET to be as high as I was calculating. So really the PET is the PET. It's really a Thornthwaite one, and in order to get to AET, I reduced it by 50% and then considered the soil moisture considerations, which really it's a very wet site. Soil stays moist all the time.
I think it would be good to have some references for having done that, the 4 and 14 inches and then map it. I mean, are these just the areas right next to the streams that are the high ET sites, or where are the high ET sites?
Yeah, there's the main ones that come to mind right now are the flat areas in the South Fork, the upper reaches of the South Fork Kartuli, that whole area north of Frying Pan Lake. And then in the Big Wiggly Basin, that's the upper reaches of the North Fork. There's a big, flat, lacustrine area in there, and it's just full of bog. And
it'd probably be good on future studies to zoom in a little bit so we can see exactly what we're talking about here, I think. And just a better discussion of, because I'm still not sure how the water balance was balanced. It says there are a variety of things that were adjusted, which is why I wanted a monthly time step so I could figure out how it was done. And I never saw that.
I saw the email, but I was on vacation.
Okay. that might have helped improve any suggestions I had, because there were it appeared as though there are 4 or 5 things that were adjusted, whether it just be the precipitation. I mean, maybe you could go through real quickly. There's precipitation from Ileana that's adjusted to help balance it. There is, I mean, why don't, can you explain?
The main change, the big picture in and out is that there's net precipitation on site, so that's precip minus the evaporation and the main out from the site is the water leaving by surface water, plus some groundwater, which really isn't a big part, under those gauges. So though the groundwater component was primarily based on what our understanding was of the hydraulic conductivity and the gradients in the cross-sectional areas under those gauges. So then really we had to adjust the precipitation in order to balance that. That's the big picture. And we adjusted that precipitation by elevation. So we applied orographic factors. And I'm not sure if I'm going to get the numbers right, but something like 10% in winter months and something like 4 or 5% in summer months.
10% of, I'm sorry.
10% per 100 meters. We increase.
Increase at 10% per 100 meters.
Yeah.
Okay.
So 1.1 every 100. You multiply it again and
Gotcha.
multiply it again. So.
Gotcha.
So that it ends up ranging in the latest models from 40, something like 40 inches to 70 inches over the study area, and then we actually we adjusted the precipitation record at Iliamna so that it would be so that we could relate the Iliamna precipitation record to the site precipitation record. So to do that, we had a different multiplication factor for the summer and for the winter, and part of that was due to the orographic factor, which more precipitation with higher elevation, and the remainder of it was due to the fact that Iliamna didn't have a windshield at all. So it had greater losses of precipitation than the Site 1 precipitation gauge did. So we increased them differently in the winter and the summer for that factor. Then when we got to the site, so now we have the Site 1 gauge more or less generated by Iliamna. And we wanted to do that because we wanted to use the Iliamna record all the way back to 42 when we're all done. So so now we have the Site 1 record, but even the Site 1 record doesn't generate enough precipitation to balance the stream flows out of the site. So we increased that again on the basis that we were seeing losses from that precipitation gauge. And I don't remember the numbers yet either, but again, more in the winter because it's much more difficult to collect horizontally flying snow than it is rain. But we again increased that precipitation Site 1 record by in order to balance the flows out of the site. And then for each individual subcatchment area, we said, okay, they're all a little bit different. We can't use exactly that at each one, so we had a local factor. And maybe it's due to measurement error, maybe it's due to rain shadow effects, maybe it's due to snow blowing from one catchment into another, those kinds of things that we were looking for. And that local factor then ranged at the present time. I can't remember exactly what it was in the EVD, but present time ranges from 0.9 to 1.1, so plus or minus 10%, which in reality is, I don't know if that's pretty good if all our stream gauging is that good. So for all of those, how many gauges do we have? There were 26 gauges that we're looking at are all adequately represented by 0.9 to 1.1. So to me, that's very, very tight, and the reality is that we have excellent stream gauging. So,
well, I mean, it did look that the the fit that you showed in the presentation here was a lot better than some of the fits I saw in the EBD.
Yeah, the methodology that we had in 2008 is a little bit different than we have now, and just in terms of how we go through the fit process. But it's still a graphical process, not any kind of a. When I tried to adopt a minimization of the errors, I just got in really big trouble.
You weren't able to write a series. You weren't able to write a water balance. Let's see, a spreadsheet optimization program
that worked.
That worked.
Yeah.
So there is a bit of subjectivity,
Yeah.
and yeah, that would be. I don't know how you document that without being really tedious, but it probably will need to be at some point. Well, I say tedious is, I mean, every one you got to.
So I have gone and talked to some
Yeah.
other people who spend their life doing watershed models, and they end up finding the same thing, that they I didn't do this, but they tend to use the automatic methods to get in the ballpark, and then use the graphical techniques to improve the fits.
Okay. Are you going to switch to using some of the irradiation data for PET, by the way? Because I asked a question yesterday.
Well, it's not difficult to do.
Yeah.
What I'll do, I guess what I better at least do is look at the answers that I get using that method.
One of the concerns that Tom brought up was not being able to access some of the basic data, and I know the request has been put in, and there's been some discussion. I was wondering if somebody from PLP might come forward and address that concern.
I was kind of the conduit. That's the microphone.
Yeah.
I'm Jason Gray from Hubble Environmental Department, and last week we received Tom's request, and I forwarded it to Hugh. Rod was out on vacation for the week, but what I understand, it was just not able to be done before now. But can you speak to that, Hugh?
Well, I sent back an email with a couple of questions of clarification. I'm just waiting for a response to that email.
I did respond last Wednesday.
I didn't receive that email.
Because I did. I mean, I had sent a. I did respond to one. You were asking which what kind of data I wanted and for what time period I think it was.
Yeah. I didn't see that email. So if it could just be resent to me, then I'll address that.
I don't know how much more I'll be going forward with. You know, we're here doing the review now, but I'll go ahead and resend it, or I would like to see it.
Sure.
So.
Yeah.
Thank you.
You recognize that we're talking about a lot of columns of data here.
Well, I think when we be talking about, let's see, each subcatchment, I'm only looking for monthly data. Yeah, I know there'd be a lot of columns.
Yeah.
Which is why I would prefer a spreadsheet as opposed to a PDF.
Oh, yeah,
a lot
well,
of PDF, but if I will.
So would I. If I were you.
I don't know what you'd do with a PDF.
That would just be an exercise in frustration.
Well, I mean, yeah, I would do a lot of looking at it, and a spreadsheet would be preferable to look at it. So that.
Are you about finished, Tom, or do you have
Well,
another?
I mean, the rest of it could just be some of the groundwater model questions that that I raised. I mean, maybe you could talk about going from 5 layers to 7 layers, and I mean, what are the thicknesses now, and how have you laid out that difference? Because the model I reviewed had a 5,000 foot thick layer 5, which was, at least that's how I understood it. One place, by the way, it said 500 feet thick, but
That'd be a typo.
It was a typo.
Yeah.
5,000 feet of just one conductivity value, and I guess I'd just like to hear how you've changed it a little bit since you now have 7 layers.
Well, in general, whenever I undertake a modeling project, particularly one of this complexity, I want to do it in increments. I don't want to start out with the most complicated model I can imagine. So I like to start out at a relatively simple level to get into the exercise and then gradually increase the complexity of the model. So as you mentioned, that model layer was created that way so that we can at least account for the fact that the pit is going to be quite deep in the first iteration of the model. And then in the next iteration of the model, we felt that we needed more discretization within the bedrock to better describe the variation in hydraulic conductivity that we see with depth. And so that's why we added some layers to the bedrock, and we took into consideration the bedrock map that you saw Rod present, and use that to inform the revised hydraulic conductivity distribution within those bedrock layers. And for that matter, we have started to do some of the assessments of the dewatering of the pit and looking at the drawdown cone resulting from that dewatering. And for the purpose of those simulations, I forget exactly what we've done, but we've added many more layers to the model. I think it's now a 14-layer model for doing the dewatering simulations, because once you get into those kinds of impact analyses, you really need to have that kind of discretization in the bedrock to be able to do those simulations in a reasonable way.
Do you have enough data to parameterize that many layers in the bedrock?
I'm sorry?
Do you have sufficient data to parameterize that many layers in the bedrock? Or are they all the same parameter? Just, I mean, in some time, do you add layers that improve the calculation?
Yeah, at this time, I mean, we're going to need to update this as we proceed. But at this particular time, for this iteration, the deeper layers in the model have the same hydraulic conductivity.
Okay. So you would have one that's, let's say it got lower conductivity down to the bottom of the tertiary, then it got higher. So you're going to have a layer with high at the top of the see, below 1,500 feet, you're going to have a layer that's a little higher, and then it's going to get lower again as it goes down.
Well, I don't know at this point. Rod and I are going to have to put our heads together and decide just how we're going to distribute that with depth. Overall, when Rod and I have been talking, you know, even though there are those isolated fractures that you see at depth within the deposit area, from my discussions with Rod, the overall transmissivity of those fractures and the ability of them to produce, you know, meaningful amounts of water seems fairly limited at this time. That's my current understanding of the conceptual model of groundwater flow within the bedrock. You know, one of the things that we recognized early on is that you know, by far the vast majority of water that we felt was entering the groundwater system can be accounted for within the local groundwater system. And our current conceptual model is that the potential for, you know, very deep groundwater flow or large inflows from great depths in the bedrock, the potential for that is very limited.
I have just a follow-up question on the layers in the model. How well do the layers that you've these are hydrogeologic units? How well do they match the stratigraphy? Are they the same? Or are they different? Or
yeah, what we did, you might have noticed on one of Rod's slides that you could see a whole series of crisscrossing lines, and each one of those crisscrossing lines represents a hydrogeologic cross section. Right. And we developed those cross sections so that all the intersections, all of the stratigraphic interpretation is consistent. And so we have this basically a fence diagram across the study area that describes the stratigraphy of the site based on all the drilling information that we've collected. Then the next step is to decide where the model layers are going to go in light of where we have those stratigraphic boundaries. Right. And of course there's lots of detail in the geologic interpretation that's not appropriate to incorporate into the groundwater model. Right. So what we choose is we choose the boundaries of the model layers to represent the most significant geologic features that we see. So for example, within a given model layer, we can expect to see variation in stratigraphy, but we capture the primary features of the stratigraphy by positioning the model layer boundaries based on the major stratigraphic boundaries.
Right, right. And how do you treat the boundaries? Are they all no-flow boundaries, or do you permit some vertical exchange? Or
between the layers?
Yeah.
Oh, for sure. There's definitely vertical flow between the layers. Absolutely.
Okay.
Yeah.
And so the last point on this is you know, right around the mine site, you've got lots and lots of data on the units and the layers and their conductivity. But what about beyond that? how would you constrain the layers and verify the model at much greater distances from the mine site?
Yeah, it's always a balancing act to decide, well, how much data is enough data?
Right.
Now, certainly the monitoring network and the number of drill hole logs that we have now compared to what you saw in the EBD has increased enormously.
Right.
So, for example, we've expanded the data set up in the North Fork Coctuli a lot. We've expanded the data set a lot down in the South Fork Coctuli.
Right.
And so, I mean, there is going to have to be a decision made at some point, is this enough data? But I feel really quite good about what we have at the moment, considering the stage we're at with the project. I mean, I've never worked on a project in my life, and I've never seen one that has the kind of plethora of drill hole information and years of monthly piezometer measurements from hundreds of piezometers. I mean, I've just never seen anything like it in my life. So we're able to, so what it all means is we're able to distinguish seasonal variations in water levels at multiple locations throughout most of the study area in multiple hydrogeologic horizons. And we're also able to, look at how the model is responding compared to the kinds of flows that we're seeing in the rivers. And similarly, like Jamie was saying yesterday, I've never seen a set of streamflow data like this in my life. So it's pretty good. I feel pretty good about it. Yeah, because we really do see differences in responses at different depths. For example, throughout the South Fork Coctuli.
Right.
And for example, you saw the difference in the watershed divide that Rod illustrated from the field data. And then when we look at the model, then we get a similar contrast in the watershed divide. And we're even able to, distinguish that the amount of water being simulated by the model going from the South Fork Coctuli into that upper Tulare tributary, it's the right number. Mm-hmm. And the heads are in the right range. So, yeah, I think it's an ongoing discussion as we proceed with the impact analysis and, address this larger question of, how much data is enough data and how much modeling is enough modeling. But I really feel quite good about it.
Just one last thing on the model layers.
Yeah.
Before you're ready, Katie. I mean, as Chris brought up there's a bit of a dip to the in the bedrock, if I'm not mistaken, and so you're going to end up with conductivity layers that have a fair amount of vertical angle to them. Am I correct in that? I mean, you see that in the multi-port.
And the tertiary is very very steeply dipping.
The tertiary is, but not the.
Well, that's not so much. You're talking about the dikes and sills, and it's quite a mishmash actually within the actual deposit area with the intrusive activity into the pre-tertiary siltstones and sandstones.
I guess the question is: are all the layers in the bedrock horizontal, or are they going to account for some of the dip?
Well, at the current time, we haven't gone to the level of detail of matching that dip, and when we get to the next iteration, then Rod and I will have to take a look at that and see if we feel that it's warranted to simulate that. Because we certainly can do that.
I mean, do you generally prefer to? I mean,
generally speaking, I prefer to.
Yeah,
yes.
I mean, you maintain the same conductivity in each layer as opposed to having a horizontal layer where you have to, do a calculation every cell to end up with a new, your conductivity.
Exactly. It makes it a lot easier to implement the hydraulic conductivity field.
But I mean, have the flow going along, parallel to the. Yeah, that's better. Okay.
Yeah. The consequences of those changes on the environmental baseline model are, you would never see them. It will be an issue when we start looking at drawdowns and inflows.
Well, I mean, the difference between 14 layers and 5 is I mean, you can do it with 14. With 5.
Katie, did you have a question or comment?
Thank you. I was wondering, you noted that the hydraulic conductivities decrease with depth in the mine, which fits preconceived notions about what should happen, and your data fit that. But my question is, when you depressurize that area by removing rock in an open pit, do those fractures or does that area become more conductive, or are they permanently shut down? Do we have any evidence to go either way?
Well, generally speaking, people believe that there's an area near the pit that will be de-stressed, and the fractures will open up a bit. I guess the jury's out on just exactly how far away that goes, but there are people who, you do a stress analysis and look at that impact and make those kinds of judgments.
So then the consequence of that, would I be correct in understanding the consequence of that might be more flow into or out of the pit area based on the decrease in stress and opening up those fractures, allowing them to be more conductive?
Generally, no. Generally, what that does is it makes a shell around the pit of higher permeability, so the apparent pit perhaps gets a little bit larger, but it doesn't make a really big difference to the inflow. What it does make a difference to is the pore pressure distribution in the pit walls, and the designers of the pit need to consider that information when they're thinking about their pit slopes.
Okay, thank you.
Just like to ask if Tom had any. No, I mean Tom L.
Yeah, I've got a few questions. I guess one has to be asked. I think I see what I expect, but Hugh, this model is basically treating the bedrock as equivalent porous media.
Yes.
Is there any reason to consider going discrete fracture network? Has there any thought been given to that? Are the fracture networks characterized? Is that on the table at all?
Do you mean actually using a discrete fracture network model?
Right.
You're just giving me the shakes here.
I said I had to put it on the table.
Yeah. Well, it's a question that always needs to be asked.
Right.
Can you just briefly explain the difference of what you're talking about here?
Yeah, certainly. What Tom's talking about is that there's a way of simulating bedrock flow where you can actually explicitly incorporate every single fracture in the bedrock or incorporate a representative set of fractures within the bedrock to actually distinguish between that part of the bedrock that has a fracture surface and then those larger blocks of the bedrock that are represented by the bedrock matrix. Maybe you want to...
Oh, that's fine.
Okay, yeah.
Yeah.
So that's the question that he's asking, is that currently we are using a model that we call an equivalent porous medium, and what that means is that we represent that system of fractures and matrix in the bedrock with an equivalent description that describes it as an overall porous medium, and that works as long as the scale on which you're developing the model is large enough that you can have enough fractures within that volume to represent it as a porous medium.
So one of the issues that Tom Meyer brought up during his presentation was these other pits where he has experience where you start pumping and you get way more water than you anticipated with your equivalent porous media approach, right? Is there any reason to think from fracture characterization activities that there are say preferred pathways such as major fault fractures? That I mean, you can discretize.
The main one would be the major fault forming the Graben on the east side. There is a major fault there, and we have done some packet tests on that, and it does have some permeability. Mm-hmm. But of course, it also has very thick gouge zone. Mm-hmm. So we think that we will have inflows along that fault that will be measurable when the pit gets to it. Mm-hmm. And we will have to consider that as a pathway before it gets to it, when the wall's close to it, as a source of groundwater pressure that we have to be concerned about.
And you'll parameterize this model to account for changes in hydraulic conductivity.
Yeah, and we may, and it may be that it's important enough that it will generate additional testing to see just how much continuity it does have.
Mm-hmm. Mm-hmm. Okay.
Yeah, so I think to specifically answer your question, the current plan is to represent the more significant structures that might provide preferential pathways within the structure of an equivalent porous medium model.
Right. So I said I saw what I expected. I just thought,
yeah.
Are you thinking at all about that? You made a comment at one point about TDS increasing versus depth, and And I don't have a strong feeling for how much it might increase versus depth, but
I just might mention at this point, TDS is a common acronym that's used, and it refers to total dissolved solids. It just means the total amount of dissolved solutes that are in the water, so which can be measured or analyzed. Go ahead, Tom.
right. So I'm just sitting here thinking, if if I think about the Canadian Shield or some of the locations where I've worked, if you get down to 4,000 feet, then you're into 100 grams per liter brines, very, very dense, heavy brines. I suspect that's not the case here, but density-driven flow, all the density stratification issues, are those
2,000 is what we're at. 2,000 is maybe 2,300 is about the highest.
grams
we've
per liter?
measured.
2,000 milligrams per liter?
Yeah.
Yeah, yeah. So,
And I'll show those data this afternoon, by the way.
yeah, I assume that we'd probably see some of that. Is it something that you're considering or thinking about taking into account from a flow point of view, just the density effects on flow and how that might be dealt with? Are you going to cause upconing, for example? Is there any of those sorts of concerns or thoughts toward them?
Yeah, for the kinds of dissolved solids that we've seen in the 2,000 to 3,000 range, I really didn't think it was necessary for density-dependent flow.
Okay. And if you're up in that sort of concentration, is it sodium chloride, calcium bicarbonate? What, I know this is going to come up later, but it does impact on the flow modeling if you're talking about pit dewatering, because that water will ultimately be transferred through to a treatment process. And some of those really soluble salts like sodium chloride are very hard to remove, so they'll be discharged ultimately, right? That's kind of what I'm getting at. So you can't remove the sodium chloride in a treatment process, I assume. So how much of that type of water might come in depends on the flow characteristics, the density, all these sorts of things. So is there any thought about that? Are we thinking along those lines at all? Is there any concern about higher TDS waters during pit dewatering and what the fate of those solutes might be?
Well, I do know that people are considering what kind of treatment technologies that they will require on the site. I can say that, not that it's fixed yet, but they certainly are considering all possible methodologies to get the water quality to an acceptable level.
That's a good introduction to this afternoon's session.